So basically we first thought, what is going to be our statement, and we actually came up with something quite quickly, I think, in the end, and which was supported by everyone, which is to develop more robust Musa systems by widening the genetic base. So actually it's quite a bit more modest, maybe than with some of the other groups, who say, well, we're going to conquer the world, productivity has to double. We actually say, no, if we can just keep what we have, it would actually be really good, because that's going to be a challenge already. Because in the end, we feel that Musa systems, they have an important buffer function in African farming systems. And basically, the problem with these Musa systems is they have a very narrow genetic base. When you look at the East African highland bananas, for example, then the Ugandans are very proud they have 100 varieties. But when you look at the genetic variability, it's extremely small. Sorry? So basically, if you look now at Musa systems, every 10 years there is a new disease coming in. People have maybe heard about BXW, have heard about BBTV. There is another one which is coming in now, tropical race 4, which is a fusarium. And that one is about to knock out all the bananas in the world, because so far there is no resistance yet found. So working with a crop which has an important buffer function, if we double the productivity of this crop, basically we're just going to flood the market. There is no elasticity here, so the prices will just drop. So there's no use in doubling the production, but just keeping that important biophysical and socio-economic buffer function that bananas have in Africa is going to be hugely important. And the biggest threat is these new and emerging pests and diseases. And every decade, thank God for the Musa scientists, there is no pest and disease. So basically, when we want to work on it, we have two approaches and two things that we work on. On the one hand, we have to work on with this genetic diversity. There is an enormous diversity for bananas in Southeast Asia, which is still poorly mapped, poorly conserved, and poorly understood. So we have to map, characterize, and conserve the wild relatives. We have to also start using, some of this diversity. For example, there's bananas with the P genome that have a tendency to be more drought resistant, for example. And we can use novel techniques in bananas, such as GMOs and market-selected breeding. So this is where we basically want to say we have to better understand genetic diversity, tap into it, and then make breeders use it. That's one aspect. And then, of course, we have the G times the E, so we also have to understand the E better. What are we doing it for? We have to understand these pest and disease constraints. Where are they coming from? What is their diversity? If we know, for example, with tropical race 4, which is this new devastating fusarium disease, where it originated from, then probably in these environments we can still find some resistant genes from the banana. So we have to understand and characterize these biotic threats. We have to understand, of course, also the abiotic stresses, water, nutrients, wind to a lesser extent, and cold and heat is less relevant for bananas. And of course, we have to understand the end user. So what are the consumer demands and the nutritional value. So our approach is basically looking at G times E. I don't think anything novel in there. Now, what are the constraints to implementing that approach? These activities on better understanding and using the G and the E. On the support side, I think there was some frustration with some of the people in the group that donors are still not understanding why our work is so important. So basically, Musa have this important buffer function in the systems, but in many cases, donors, particularly coming from Western countries, when they think banana, they only think Chiquita banana from the supermarket. And of course, they don't appreciate how important it is as a staple food for much of West and Central Africa and East Africa. So there's a feeling that we have to get more support on that side, particularly also because, of course, it's a very slow crop. It takes 15 years to do any classical breeding to get the chance of having the first product. Then there is big policy constraints. We talked about these wild varieties that are there in Southeast Asia that could help African breeders to actually make it much more robust. But getting these varieties and these genes, to actually move to other countries is a huge problem because of policy, material transfer agreements, political issues, countries not wanting to give away their germplasm, of course. There is a policy constraint to GMOs. Bananas and GMOs go well together because it's a sterile plant, and particularly in Africa, of course, it's not native to Africa if you go far enough back. And so at least, it's interesting to work with GMOs because you have a small genetic base, because it takes so long. And because it's a sterile plant, it has many of the benefits which other crops wouldn't have. But still, you need to have the support policies to start using GMO technologies and implementing them. And then, of course, once we have the products, we have to think about appropriate seed systems and, finding technologies to match technology to user limitations and preferences. So that's on the support side where we have problems with activities. When it comes on the technical side where we have problems is that there are very limited so far Musa conservation tools and capacity. Even to conserve the vegetatively propagated crops like Musa is quite complicated. It's not just a seed that you put in a vault and you just leave it there for 50 years. There is a problem when we want to use, for example, this bee genome. That bee genome has in it BSV, which is a banana streak virus, and that virus is coming out again and expresses itself once it's put under stress, or even often when you use it in tissue culture in the lab. So this is really a constraint to using that genetic diversity. And then we have very limited capacity so far on environmental modeling, including climate change modeling for bananas. There's very little understanding of crop physiology of bananas. When we are talking about banana and crop physiology publications, there are 3, 4, maybe 5 people who have ever done anything on it, and that's it. So we are very far away from what, for example, is happening in rice. And so there's also very little reliable data. Okay, then we still had a discussion about, and I didn't manage to put that in the computer, but about a whole series of constraints. Abiotic constraints such as drought and soil fertility, but also biotic constraints. And now for the 3 major ecoregions where bananas occur, which are mostly, by the way, the humid highlands, the humid lowlands, and of course there's a little bit of bananas in the, let's say, the savanna areas. We mapped these areas as well, and you can see them here. So this is the humid lowland, these are the humid highlands, and this is the savanna area. And of course, we have breeding stations here from IITA in Karbab, and here from Nauru and IITA in East African Highlands and in the lowlands. There is no breeding going on in the savanna area in Africa. But what we wanted to do now is for each of these areas, we have said, okay, what are the key constraints and how are they at the moment for productivity? So we gave the rank 1 to 5, 5 being extremely important as a constraint to limit yield, and 1 being there that, not important at all. And then we gave indications with arrows, how these would evolve in the future. What you see in these graphs is basically with climate change, the biggest step is not so much the drought, but it's actually really the pest and diseases in the banana systems, both in the humid highlands as in the lowlands. We see that's where the arrows are still. The very biggest threats really are in these diseases, which actually they're not climate related, sorry. They're not climate related, but they can really be devastating. So we have climate related changes, such as in nematodes, weevils, and Sigatoka. But we also have some diseases which their evolution is not related to climate, but we predict huge, potentially catastrophic events, which may occur. And having that small genetic base, there is a big risk that one of these things is going to happen. If one of you is going to China soon, on holidays, then when you come back to East Africa or West Africa, please, go with your shoes in some water with chlorine in it, I don't know how you call it here. Or even throw the shoes away, leave them in China, go with your socks in the airplane. Because one day, somebody will come from that area, will have the spores of tropical race 4 Fusarium on their shoes, walk in East Africa, and so far there is still no resistant discovered for this Fusarium race, this Fusarium tropical race 4. And if that's going to hit East Africa before we are ready, we're done.